In this lecture, we'll go over the delta method. The delta method is a useful tool to have in the toolbox for estimating the variance for functions of parameters. For example, the delta method could be used to estimate the variance for the product of time-specific survival estimates over the time horizon of a study. I'll begin with simple linear transformations, go over transformations of multiple variables, and finish with an example using Program R. To begin, let's look at a transformation of a single random variable x that is approximated by a normal distribution with a mean of 10 and standard deviation of 2. Now let's review functions with the scalar constant a. The expected value of the function ax plus b can be expressed as the constant a times the expected value of the random variable x. The variance of the constant equals 0 by definition, and the variance of the function can be expressed as a squared times the variance of x. Given that x is a normal with a mean of 10 and standard deviation of 2, what is the mean and variance for y based on the linear transformation 4x plus 3? Plugging in the values of x into the scalar functions for the mean and variance, the expected value of y is 43, and the variance of y is 32. Now let's turn to a more general theory for the transformation of a single random variable. For y as a function g of x, we can use the Taylor series expansion to estimate the variance of y. Let's define the notation going forward. The expected value of y equals a function for the expected value of the random variable x, and we will call this function g of mu. Here the variance of y equals the square of the first derivative of the function g of mu times the variance of the random variable x, where the first derivative of g of mu is the partial derivative of g of mu with respect to random variable x. Therefore, the variance estimator for the expected value of y is the square of the partial derivative of g of mu times the variance of the random variable x. Here are some examples of the expected value of parameter y given a function of a single random variable. Y might be an availability parameter as a function of gamma, 1 minus gamma, or y could be a function of survival, such as survival squared, or y could be a function of abundance, where abundance is divided by a constant a. In all these cases, we can use the linear variance estimator for the expected value of parameter y. Powell in 2007 is a useful reference for the delta method. We can extend the delta method to estimate the variance for a function of multiple variables. Here, g of theta is a function of the product of theta 1 and theta 2. Then, using matrix algebra, the variance for g of theta is the vector of partial derivatives of g of theta with respect to theta 1 and theta 2 times the variance covariance matrix times the vector of partial derivatives transposed as shown here. The variance covariance matrix has variances for theta 1 and theta 2 on the diagonal and covariances between the parameters on the off diagonal. Here is an example for the product of survival probabilities S1 and S2. The variance for this function equals a vector of partial derivatives for g of s with respect to S1 and S2 times the variance covariance matrix times the transposed vector of partial derivatives. The matrix formulation can be expressed as a linear equation shown here. With more than a few parameters, this can get complicated quick, but luckily software such as Derive or MATLAB can calculate the linearization easily. Interestingly, if the survival estimates are independent, then the linear equation simplifies to this expression. What we mean by independence is there is no covariance between the parameters, shown by zeros in the variance-covariance matrix, and this can come about if S1 and S2 are estimated from different models. We can retrieve the variance-covariance matrix in MARC by navigating the output drop-down boxes shown here. The DBase file gives the greatest number of significant digits. This slide shows an example of a variance-covariance matrix. The values highlighted in yellow are the variances for the parameters on the diagonal, and the covariances between the parameters are shown on the off-diagonal. The variance-covariance matrix can also be written to a Notepad text file. Here, matrix 1 refers to time-specific parameters for age group 1, and matrix 2 refers to those of age group 2. Make sure you understand what the highlighted values represent. Here is a delta method example for the product of parameter estimates using program R. I recommend copying the script into R and becoming familiar with the calculations. U1 is the estimate for parameter 1, U2 is the estimate for parameter 2. This line contains the function for theta as the product of parameter 1 and parameter 2. These lines house the variance-covariance matrix. Here is the partial derivative for the function u1 times u2. And here is the delta method calculation for the standard error of theta. Easy, huh? At this point, we could use theta and the standard error of theta to build a normal, symmetric 95% confidence interval. However, with these parameter estimates, the confidence interval produces negative lower confidence limits. And we want the confidence interval for theta to be greater than 0. So this example shows how we can use our new friend, the delta method, to produce back-transformed confidence intervals on the 0 to 1 scale. So here's the sign transformation for theta. This is the partial derivative for that sign transformation. Here is the standard error estimated on the sign scale. And then here are the confidence intervals estimated on the sign scale. And then we back transform these into the probability scale in these lines here. So again, I recommend trying this in R. And then this example uses a sign link, but how would we do this for a logit link?